In this video, I'm going to discuss chemical equilibrium. To begin with, I'm going to put up a generic reaction scheme like this, where I've got reactants called A and B. I've just got twice as much as B in this reaction, and they react to produce C and D. The delta H, which is the enthalpy change for a reaction, is minus 100, so we know the reaction is an exothermic reaction. So just going back to our energetics topic, in terms of an energy profile diagram, what this means is that my reactants have a certain energy, A and B, okay, and what happens on going from A and B to C and D, there's a release of energy. So if this is our energy, as A and B have a higher energy than C and D, when we work out the energy change overall, what we see is there's an excess of energy which gets released into the surroundings. So that's just shown by a negative delta H there, because delta H stands for the energy of the products minus the energy of the reactants. And if the energy of the products is lower than the reactants, which you can see from the scale, we get a negative enthalpy change, and that results as an exothermic reaction. For more on energetics and energy and chemical reactions, see the energetics video. Now let's discuss this reaction. First of all, we notice that we have a different arrow. Okay, we don't have our conventional arrow from reactants going to products. These are our reactants and these are our products. These arrows stand for what is known as a reversible reaction. So this is basically a reaction where products can, actually under certain conditions, turn back into reactants. We can look at A and 2B here as being reactants going to C and D as products, but also what actually is happening in this reaction is C and D also react to form A and 2B. So both the reactants, both their products, depending on which way you're looking at the reaction. The forward reaction is this way, so denoted by this arrow here, and the backward reaction goes that way, and that's just denoted by that arrow here. Okay, when discussing chemical equilibrium, we often describe a closed system. Now, a closed system is one where we have no substances being added or lost from the chemical reaction itself, but energy can be transferred in and out. So heat can be transferred in and out, light can be transferred in and out. So what I've said here, no substances go in or out from the reaction, only energy gets transferred. So the next thing we need to discuss is what's known as a dynamic equilibrium. Okay, this is an equilibrium that exists in a closed system when the rate of the forward reaction is equal to the rate of the reverse reaction or the backward reaction. So, just to recap, dynamic equilibrium is an equilibrium in a closed system where the rate of the forward reaction is equal to the rate of the reverse reaction. Remember from the rate section and the rate video that the rate of reaction is the change in concentration of reactants or products over time. So what we're basically saying is these particles are constantly reacting. The rate of the forward reaction is going to be equal to the rate of the backward reaction when the system is in equilibrium. Okay, the equilibrium part means that the concentration of the reactants and the products don't change. We might then infer that they're just sitting there not doing anything. That's not true. They're constantly reacting. But the key difference here is that they're reacting at the same rate. So as A and B react to form C and D, at the exact same rate, C and D are reacting to form A and 2 of B. So equilibrium because of this, and dynamic because the rates of both reactions are the same. Some people like to think of it as being like a state of balance or like a seesaw because things are balanced. I don't like that because things are constantly moving. So an analogy that I'll use is the image of a person going up an escalator the wrong direction. So if I focus in on the image on the right, what's happening there is there's a person walking up the escalator and the escalator is traveling down. Now, if you want to get to the top of the escalator and the escalator is traveling down, you'll know that you need to be traveling faster than the escalator. So this blue line needs to be happening a lot quicker than this purple line here. In our analogy, what that basically means is that the rate of this forward reaction is happening much faster than the rate of the backward reaction, which is the purple one there. So to get from the bottom to the top, if the travelator is going down, you just need to be going quicker. So if this was happening in my reaction here, A and B would be reacting to form C and D at a faster rate. So that would be the blue line there. At a faster rate than C and D were reacting to form A and B. But think about it. If A and B are reacting at a faster rate to form C and D, then C and D are reacting to form A and B, then we don't have a system that's reached an equilibrium, because sooner or later A and B will react and there'll be no more A and B left. There'll be just C and D. We can't have two reactions happening at the same time there, because we'll have run out of A and B because it's happening at a faster rate. So the image of the escalator gives us a fairly good idea of where the reaction is in terms of progress, i.e., is there more products in the traditional sense, or is there more reactants? So a closer way of looking at that is called the position of equilibrium. Position of equilibrium is a reference to the proportions of the various species in the mixture. Right? So we may have more reactants, or we may have more products in the traditional sense. So let's have a look at it in this way. If I drew out a line like this, my position of equilibrium could be here, over to the left. Let's say this is my midway mark here. So this green line represents the fact that I've got 50% products, 50% reactants in the traditional sense. But if, let's say, my position of equilibrium lies over here to the left, that basically means this person here in the travelator or the escalator is pretty far down. Okay, so he's not quite up the top, or she is not quite up the top. They're about a third of the way up, let's just say. So this means the position of equilibrium is over to the left. This effectively means that there's more A and 2B. If it's over to the left, then there's going to be more of A and 2B. Let's look at it and see what happens if the position of equilibrium is over to the right, like that. Then there's more of C and D.